morning students, welcome to Lakshya Academy YouTube channel. This is the second class. Yesterday we discussed of crystalline solid and amorphous solid. So I have given the pictures of crystalline solid and amorphous solid. Observe the diagrams carefully. You can understand how atoms bound in that crystalline solids and amorphous solids. And these are the two examples of crystalline solids and amorphous solids, and they are the particles. Today our topic is energy band in solids. According to quantum mechanical laws, the energies of electrons in a free atom cannot have arbitrary values, but only some definite values. If an atom belongs to a crystal, then the energy levels are modified. This modification is not appreciable in the case of energy levels of electrons in the inner shells, that is, completely filled shells. But in the case of outermost shells, the modification is appreciable because the electrons shared by the neighboring atoms, and due to the high electric field between atoms and the shared electrons, energy levels are split up and spread out, forming energy bands. Consider a single calcite crystal, single silicon having capital N number of atoms. Atomic number of silicon is 14 and electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p2. And this is the brief explanation of energy formation of energy bands in solids. After that, we discuss in detail. To understand, first I explain something about Rutherford's atomic model. According to Rutherford's atomic model, every atom consists of electrons. These electrons revolve around the positively charged nucleus in a specific energy levels. Those are called as orbits or shells, and the angular momentum is quantized for each electron. The orbit number can be characterized by the principal quantum number. The concept of fixed energy levels is valid only when an atom is isolated from the other atoms. But in the case of solid, atoms are closely packed, so the energy levels overlap each other. Okay, this is a small video to understand how energy levels and electrons revolve around the nucleus. Next, I explain the formation of energy bands in solids by using a simple graph. A graph is drawn between interatomic spacing and energy of the orbits by taking interatomic space along x-axis and energy along y-axis, and those are the energy levels. We consider silicon 1s2, 2s2, 2p6, 3s2, 3p2. And students observe that, and I have taken 4 points on interatomic spacing axis A, B, C, D, and observe carefully the red part of the graph. and I explain the formation of energy bands in by considering 6 different cases, and after that I explain the concept of valence band, conduction band and forbidden energy gap. Consider the first case, the interatomic space R equal to OD, that is far greater than OA. Observe the graph carefully. Each of n atoms has its own energy levels. The energy levels are identical, sharp and distinct. The outer 2 subshells of silicon atom, that means 3s and 3p, contain 2 s electrons and 2 p electrons. So there are 2 n electrons completely filling 2 n possible s levels. Note down that 2 n electrons completely filling 2 n possible s levels. And out of 6 n possible p levels, only 2 n are filled and all the filled p levels have the same energy. Students, observe carefully. Out of 6 n possible p levels, only 2 n are filled and all the filled p levels have the same energy. Okay, 2 n electrons completely filling 2 n possible s levels and 6 n possible p levels, only 2 n are filled and all the filled p levels have the same energy. The second case, R is in between OC and OD, that means OC less than R less than OD, and between OC and OD, if we observe carefully the graph, there is no visible splitting of energy levels, but there develops a tendency for the splitting of energy levels. Tendency of splitting of energy levels. There is no visible splitting, but there is a possibility of splitting of energy levels. Next, third case, when R equal to exactly OC, the interaction between the outermost electrons of neighboring silicon atoms becomes appreciable and the splitting of the energy levels commences. Here, the splitting of energy levels commences when the interatomic space R is equal to OC, and I mention in the graph OC. Here, the splitting of energy levels commences. Next, fourth case, dear, when R is in between OB and OC, OB less than R less than OC, the energy corresponding to the S and P levels of each atom gets slightly changed. So, corresponding to a single S level of an isolated atom, we get 2 n levels. Note down that single S level of an isolated atom, we get 2 n levels. Similarly, there are 6 n levels. And fifth case, when R equal to OB, the energy gap disappears completely. 8 n levels are distributed continuously. We can only say that 4 n levels are filled and 4 n levels are empty. Out of 8 n all the levels, 4 n are completely filled and 4n levels are empty. So all the energy levels distributed equally. Energy gap disappears. There is no energy gap. Next, sixth case, when R equal to OA, the band of 4n filled energy levels separated from the band of 4n unfilled energy levels by some energy gap. This energy gap is named as forbidden energy gap. So here two bands are formed. The lower completely filled energy band is called as valence band. Upper unfilled band is called as conduction band. Students, once again I have given all the 6 levels, so it is easy to note down. The first case R equal to OD, far greater than that of OA. 2n completely filling 2n possible S levels. Okay, there are 2n electrons completely filling 2n possible S levels, and out of 6n possible P levels, 2n are filled. And second case is OC less than or less than OD. There is no splitting of energy levels, but there is tendency of splitting of energy levels. Tendency. When R equal to OC, interatomic spacing equal to OC. OC is I mentioned in the graph. The interaction between the outermost shell electrons and neighboring silicon electrons appreciable, and splitting of energy levels starts. Splitting of energy levels commences at this position. Yeah, fourth case, we move to fourth case, OB less than or less than OC. The energy corresponding to S and P levels gets slightly changed. So corresponding to a single S level, we get 2n levels. Similarly, there are 6n levels for a single P level of an isolated atom. Totally 2n plus 6n, 8n levels of same energy. Here n is very large number, 10 power 29 atoms per meter cube. So the energy levels due to the spreading are very closely spaced, and the spacing is 10 power minus 23 electron volt for each 1 centimeter cube crystal. Finally, the collection of very closely spaced energy levels is called an energy band. Next case, when R equal to OB, the energy gap completely disappears. So totally, finally, there are 8n levels. They are distributed continuously. 4n levels are filled and 4n are empty. The final case, sixth case, when R equal to OA, the band of 4n filled energy levels is separated from the band of 4n unfilled energy levels, and there is energy gap between these filled energy band and unfilled energy band. The lower completely filled band is called as valence band, and the upper unfilled band is called conduction band. If the bands in a solid are completely filled, the electrons are not permitted to move about because there are no vacant energy levels available. So this is the explanation of how a valence band and conduction band, and the energy gap between the conduction band and valence band is forbidden energy gap. This is the second part here.